Okay, this is the last problem, which is sort of an interesting little bit of physics. You've got this cue ball. This is a pool table. You've got a cue ball shot with this initial velocity. It's a speed v naught at an angle theta from the horizontal or from x. So we're going to say this is the x-axis, this is the y-axis. And the cue ball, this is where the cue ball is when it hits what I'm going to say is an 8 ball. Okay, so maybe I'll just darken that up a bit to show it's an 8 ball. And when they hit, the axis of the collision is right along the x-axis. So this is the axis of collision, which means the impulses on these go this way, right? Okay, so what we want to show is that the two balls break at right angles. So afterwards, the cue ball's velocity at the end and the 8 ball's velocity at the end make right angles with each other. That's what we want to show. So we are told it is a completely elastic collision. Completely elastic collision. What does that mean? What it means is that kinetic energy is conserved. That is what a completely elastic collision is. It's a collision in which kinetic energy is conserved. Okay, so what that means is EK at the beginning should equal EK at the end. So initially the 8 ball is at rest, right? That's one thing we know. The other thing we know is, because this is a collision, that momentum is also conserved. And that's a vector quantity. So that actually gives us, this is a scalar quantity. This gives us one equation. Knowing that this is conserved gives us one equation. Momentum is a vector. And since we're dealing with a two-dimensional problem here, if we know that momentum is conserved, we actually have two equations there. So I'm going to do two different states of the system. Okay, so state 1 is when this ball is approaching the 8 ball. 8 ball is still stationary when the cue ball is approaching. And 2 is after they've collided, and so there's some VC. I'll say VC V vector. I'll say the vector VC. Final, and this is going to be the vector here. This may be vector V8 final. Okay, so the final velocity for the 8 ball is V8. Final velocity for the cue ball is VC, and I'm going to say initial velocity for the cue ball is going to be UC. Okay, so let's look at state 1. State 1, we have momentum, and that is going to equal mass of the 8 ball times initial velocity of the 8 ball plus mass of the cue ball times initial velocity of the cue ball. Well, the 8 ball is at rest initially, so this part equals 0. Okay, and then mass of the cue ball times initial velocity of the cue ball. Well, initial velocity of the cue ball is this, I said it was V naught. Maybe I should have said it was U naught, but whatever. Okay, at an angle theta. Okay, which means that the component in this direction is V naught cosine theta, and the component in this direction is V naught sine theta. This is just simple breaking down of vectors. This is the angle theta with the horizontal. So if we want to put directions on these, make these actual vectors. This is I hat. Remember, I hat goes in the positive x direction, and this is j hat, which goes in the positive y direction. So what we have here is mc. So this is the mass of the cue ball times. Actually, what I can do is say mc v naught times cosine theta times I hat plus sine theta times j hat, and that is going to be our initial velocity, our initial momentum. It's mass times speed, and this is just the direction angle, but mass times this is velocity here. Okay, so and then initial kinetic energy is going to equal the kinetic energy for the 8 ball is 1/2. Well, so 1/2 m8u8 squared, but that's 0. So I probably shouldn't have even written that, but plus 1/2 mc v naught squared. I'm just gonna whatever. Okay, so ek. So really, kinetic energy is 1/2 mass. We know the mass of the cube. I'm sorry. Masses of these are just m. These have the same mass. I don't know. I'm sorry. I'm spacing out today. I don't know why I'm subscripting things that don't need to be subscripted. So this is just m v naught squared is our initial kinetic energy, and this is our initial momentum is just this. Okay, so great. Now afterwards, okay, afterwards we're going to have, and this is where it gets interesting. Afterwards we're going to have momentum be conserved, but let's find our momentum afterwards is going to be equal to mass of the cue ball, which is just m, as I said, times this VC, plus mass of the 8 ball times V vector 8. And that is also going to equal this. That is, and right, so we'll set those equal in a minute. And then final kinetic energy is going to equal 1/2 mass of the cue ball times VC squared. This is the magnitude of this, okay? And then the mass of the 8 ball is the same, so I'm just going to tack it on here, V8 squared, okay? So this is, and this is going to equal this, okay? So let's look at where these two equations take us. Let's look at where conservation of energy, conservation of EK, conservation of kinetic energy, which we have because it's a perfectly elastic collision, is this and this, okay? So we get 1/2 m v naught squared equals 1/2 m vc squared plus v8 squared. And what that gives us then is that we can cancel the 1/2 m from both terms. And what we get is v naught squared equals vc squared plus v8 squared. Okay, so that's that's where our first equation takes us. Okay, second equation. Our second equation we get is from conservation of momentum. And what that tells us is that this here, so m times v naught times cosine theta times I hat plus sine theta times j hat, okay, that is our initial momentum, is going to equal final momentum, which is going to equal mass times, I'm just going to stack these together, Vc plus V8. Okay, so this comes down to, what this comes down to is basically, well, let's see, we can from here we can actually cancel the m's, and then we get and take these by, let's see, how do we want to do this? So then we got v naught times cosine theta times I hat plus sine theta times j hat equals Vc plus V8. Okay, now I'm trying to remember where this goes. This gets very tricky, but it can be done. What I'm going to do, and this is kind of the part I have to pull out of my ass, but we have our two equations, okay? I mean, it's not pull out of your mass, but you got to sort of see a trick, okay? So, with this is what we got from kinetic energy conservation, okay? Is this V naught squared is Vc squared plus V8 squared. This is what we got from momentum conservation, okay? Now, here's what I'm going to do. I'm going to take this equation, this is our momentum, and this is momentum. I'm going to dot this equation with itself. What that means is I'm going to take the left side of this equation, and I'm going to dot it with the left side of this equation, and I'm going to say that's equal to the right side dotted with the right side. So, V naught, so what this is going to, trust me on this, V naught cos theta I hat plus V naught sine theta j hat, okay, that dotted with itself. So watch this, okay, copy, and then paste, I hope. Yeah, there we go. Okay, this dotted with itself is then going to equal Vc plus V8 dotted with, and I'll just write this out, it's faster, plus V8. I know. and this is going to seem strange, but trust me, it's going to work. So we do the dot products. Okay, so now this is first, outer, inner, last. This is FOIL. So let me let's go to brown here. Okay, so v naught cos theta I hat dot v naught cos theta I hat. We're doing first. Okay, I hat dot I hat is 1. This term is going to be v naught squared cos squared theta. Okay, now we've got outer, this term with the I hat in it times this term with the j hat in it. I hat dot j hat equals 0. Remember, I hat dot I hat equals 1. J hat dot j hat equals 1. I hat dot j hat equals 0. So this term dot this term equals 0. That's outer. Inner, j hat dot I hat equals 0, right? And so then at the end we get v naught squared. This is the last term. Same term, and we dot it, and the j hats become 1. Sine squared theta. Okay? So that's the entire left-hand side of the equation. Now over here we get VC, the vector VC dot vector VC. And that is just equal to the magnitude of VC squared. Remember, you dot any vector with itself, you get the square of its magnitude. Okay? Then we do outer. We do VC dot V8 plus this is inner now, V8 dot VC plus V8 dot V8, which is V8, magnitude of V8 squared. Okay. Now, you probably realize that cosine squared plus sine squared equals 1. So this left side is just V0 squared equals, and I'm going to pull some things in different order here, but VC squared. And so remember, this is speed, original speed of the cue ball. This is final speed of the cue ball plus speed of the 8 ball squared. These are all squared, okay? Plus, and this is VC dot V8 plus V8 dot VC. These are actually commutatively identical. Commutative property applies to dot product. So this is 2 VC dot V8. So we have this equation here, but what I want you to look at is compare this, okay, this purple thing, to this purple thing up here, where we see V naught squared is VC squared plus V8 squared. That's from our kinetic energy balance. So, because these things are all equal, that's this stuff right here, which means then that 2 VC dot V8 must equal 0, which means VC dot V8 equals 0. I mean, anything's equal to 0, then half of it's also equal to 0, right? And since this is the final velocity of the cue ball, this is the final velocity of the 8 ball, the dot product of them is equal to 0, which means they are perpendicular. Final velocity of the cue ball and final velocity of the 8 ball are perpendicular. And this is a fact that if you have two objects of the same mass and they collide with each other, so let's see, let me specify this exactly. Two objects of the same mass, they collide with each other in a completely elastic collision, and one of the objects is stationary before the collision, then they will break at right angles. So VC will go straight up here, and V8 will go this way. And it makes a little sense because you can think about the direction of the impulse here. When these collide, you know that this thing is going to, the only impulse here is going to go horizontally, so it's going to push this one this way, and then you could solve, and find that VC has to be going up. But it's a fact that's incredibly useful in the game of pool. This is how pool players plan their shots. They look at where the cue ball, what the relative position of the cue ball is going to be to the ball it hits, and they know it's going to drive the ball that it hits is going to be driven exactly along a line, intersecting their centers when they collide. So, useful fact. You can use your TJ physics knowledge to amaze people when you play pool, I guess.